what is spin? And the other day we left off with this gentleman. His name is Richard Feynman. And they asked him, what is spin? He could not tell us. He had no idea what spin is. He was a Nobel Prize, I think 1965. We got his Nobel Prize for QED and quantum electrodynamics, and he invented this space-time diagram, all this nonsense that they have in quantum mechanics. But he could not tell us what this feature, which has been around at least since the 1920s, if not earlier, called spin. They were thinking that electrons spin, especially the electron, right? And so they were thinking it was like a top. They said, okay, top spins and the electron spins, okay? So that was the original thought, and the word stuck. They said, okay, spin, right? Turns out that they eventually discovered that spin is not spin, okay? That spin is not like, you know, what you have with a little top, right? And so then what is spin? Because they could have changed the name if they found out it was something different. If it was, I don't know, torque, you would call it, okay, we were wrong, it's not spin, it's torque, for example, right? Or jumping up and down or whatever. They said instead the electron doesn't spin, it jumps up and down. Okay, great. But so what is spin? If it's not spin, you know, like a top, what is it? And of course, since good old Feynman, you know, he was in the 60s, you can say, well, we've evolved since then. That was 60 years ago. Okay, so let's see what spin is today. We have this gentleman. His name is Matt O'Dowd. Okay, and he asked the question, what is spin? Okay, and so how does he answer it in general terms? Well, he says, we've established that quantum spin is very weird. Man, that's a very bad way to start a presentation. Because when he says it's weird, he's not being truthful. He's saying they're ignorant. They have no clue. That's what he's saying. But he says it's very weird. That's not the right way to put it. Okay? You got to say you're ignorant and you don't know what spin is. That's the correct way of saying, not weird. Okay? Because if it's just strange, you would say, well, you know, it's not the spinning of a top. It's like jumping up and down or torquing or something else. That's not what he's saying. He's saying we don't know. Okay, and says electrons have spin but aren't really rotating. No one understands quantum spin. Right, so don't tell me it's weird. Tell me that you don't know. Okay, weird means that, you know, in the language of mathematics, when they say, oh, there's a paradox, it's weird, means that they don't know squat. That's what they mean. Okay, that's what they're telling you in your face. And then you have people who listen with half an ear and they say, oh, they really know because otherwise computers wouldn't work. Yeah, tell me about it. Okay, computers wouldn't work, but quantum says that a particle can be at two places at once. Is that why computers work? Or is that what computers prove, that a particle can be at two places at once? That's the explanation they give. When you put them against the wall and say, but that's nonsense. How can a particle be at two places at once? Well, we don't understand and we don't care about that because that's philosophy or philosophy of physics, philosophy of science. What we do is math. We do equations. Okay. So why did you even attempt to give me a physical interpretation, right? If later on you're going to tell me, well, we don't understand it and we don't care about that anyway. It's not in our job description. We don't do those kinds of things. That's philosophers on the other side of campus. So why did you try to give me philosophy, right? Philosophy of science, philosophy of physics. Why did you even attempt to give me a physical interpretation if you're going to give me a nonsensical one and then say, well, we don't care about that anyways? You know, you should stick to math. If you're going to do math, do math. Don't jump the fence into physics. That's the issue. Okay, so what does he say? Well, here Mr. O'Dowd says, this is spin, you know, and there you can see what he's doing. He's really spinning that cube, right? And he's suggesting that there's this field that is being torqued all around, you know, the cube there. But the cube is spinning. I want you to focus on that. He says spin is not spin, but he is illustrating this as spin. You can see the ball there is spinning, okay? And so he's saying, well, what it does, it kind of torques the field around it. Okay, great. We don't know what those lines are, those ropes, those cables, whatever those things are, right? These strings. Okay, but he says they, I guess, they come all the way to the electron, and so the electron is spinning and twists these things around. And so, what are those lines? I mean, I don't see them in the standard model. What are those lines that he just put in there by hand? He put them in there. He doesn't explain what they are. He doesn't tell you, like, oh, by the way, those lines there, they're this. They're strings, or they're, what are they? He just puts them in by hand, saying they're attached to this thing that's rotating, spinning, right? Rotating around its axis. And if it's rotating around its axis, yeah, it is spin. So he's saying, we don't know what spin is, but I'm going to illustrate it as, like a top would spin, right? He illustrates it like this, He illustrates it like that, but then he says, that ain't so, and don't take what I just showed you literally. But then he does spin it. He spins the cube, he spins the ball, right? And so you say, well, what does your atom look like? Does it have all these little strings attached to it or whatever? No, this is his atom. He shows the atom, okay? And it's the standard model that you'll see out there, the planetary model. That's what they always show. Okay? They show a ball in the center, which is supposed to be the positive proton, and the electron, somewhere around the proton. And the white line there going around, that's put in there because it suggests to you that the electron is going to go, that's the orbit of the electron. And they call that line an orbital, orbital, or you can call it an energy level, whatever they want to call it. But they always put that in there to suggest that the electron always goes around or somewhere around the proton. Okay, so this is the official atom. And when you say, well, is that the atom, the quantum atom? That's when they say, well, no, it's not. You're not supposed to take it literal. We don't know what an atom looks like, they say. Okay, but they always illustrate it as a planetary model. We've inherited that from good old Niels Bohr and Rutherford, Ernst Rutherford. Okay, we have another guru. His name is Derek Muller, and he's confirming what this other fellow, Matt O'Dowd, said. He shows electricity here. And what is he showing? He's showing a positive proton, right? And the negative electrons moving from proton to proton, from atom to atom. So he thinks of electrons as little beads that flow, and he calls that electricity. In fact, he says a copper wire consists of positive metal ions swimming in a sea of free negative electrons. If there were a current in the wire, the electrons would just be what? Drifting in one direction. So he's saying that electricity is what you see there, the flow of electrons, many of them, from atom to atom. And so this assumes a planetary atom. So the planetary atom is confirmed. It is the official atom of quantum, which is subsequently denied. Okay, they deny this atom. First, they show it to you. They say this is what an atom looks like, a little bead going around. This is what electricity looks like, the flow of electron beads from atom to atom. And then at the end of the show, they say, by the way, all we talked about today, forget it. None of it is true. We have no way of illustrating. We have no idea what electricity is. We have no idea what an atom looks like. So they illustrate it, and when you call their bluff, they say, oh, by the way, that's philosophy. Okay, but yeah, here you have the atom, okay, that good old Rutherford and Bohr invented. And that's the one we use today. You have the electron bead jumping from energy level to energy level, or orbital to orbital, and it's somewhere around. It doesn't have to be a planetary sense in the sense that it has a fixed orbit. It just goes back and forth. It's somewhere around the proton. That's the only change they made to the Rutherford-Bohr atom. Okay, but essentially it's electron bead negative, right, which is somewhere next to the proton center. positive proton center. And so the question is, why doesn't that bead, the blue bead, the electron bead, why doesn't it spontaneously drift away, or why doesn't it spontaneously fall into the positive nucleus? Because if it's negative, you would think it's attracted by the proton, right? And so they never explain that. They don't know what keeps the electron faithful to the nucleus. And that's the whole issue. They've never answered the question, which was how they started this issue. They started talking about the atom, the beginning of the century as a planetary atom. It came, some studies by Bohr originally and then by Rutherford, primarily those two. And they eventually concluded that it's this planetary atom, and we've never gotten away from that. We always represent the atom as the orbit, as the planetary atom. Okay, and then obviously that's when they deny it. Okay, so here we have the Wikipedia, and this is what Wikipedia tells us about spin. Spin should not be conceptualized as involving the rotation of a particle's internal mass, meaning, a top spins. That's not what they're saying. As ordinary use of the word may suggest, spin is a quantized property of waves. Oh man, the waves are spinning. And what are waves? Well, there are a bunch of vectors. That's what a wave is. You look at especially the electromagnetic wave, all those arrows, those InGen arrows that they illustrate, those are vectors. What's a vector? Is it an arrow like an InGen arrow? No, it's magnitude and direction. Okay, so especially magnitude. Okay, the very earliest models for electron spin imagined a rotating charged mass, but this model fails when examined in detail. The required space distribution does not match limits on the electron radius. The required rotation speed exceeds the speed of light. Okay, that's why they figured out that spin is not spin, okay, like a top spin, because it would violate some cherished laws of mathematical physics. The classical analog for quantum spin is a circulation of energy. So now we have this thingy called energy, which is a mathematical concept. It's just a number followed by a unit. That's what energy is. You can have I used to work with kilo electron volts. The big accelerators, they work with giga and maybe even tera electron volts. Okay, so they're talking about a concept, a mathematical concept. That's why they say the circulation of energy. How can a mathematical concept circulate? And yeah, they use these euphemisms, and that's why people don't understand a lot of this stuff, because it's not like kindergarten stuff where you get a block and you say the block moved from here to there. They can't do that with quantum. What they do is they talk about math. They say, we have this number plus a unit, and it circulates. Or momentum density in a particle wave field. A particle wave field. Particle is not a particle. Wave is a concept, and field is a concept. So far we have nothing in front of us. We have a mathematical concept. Spin is essentially a wave property. Yeah, meaning it's a mathematical property. Spin belongs to physics, whereas wave belongs to math. And never the twain shall meet. As the name suggests, spin was originally conceived as the rotation of a particle around some axis, right? Like the top. Historically, orbital angular momentum related to particle orbits. While the name based on mechanical models have survived, the physical explanation has not. In other words, they kept the word spin, but it ain't spin. Quantization fundamentally alters the character of both spin and orbital angular momentum. Since elementary particles are point-like, right? They're point-like, meaning they're made of a single piece. That's what they're trying to say there. Okay, point-like means it's not made of any particle. It's an elementary or fundamental particle, meaning it doesn't have parts. Self-rotation is not well defined for them. No, it's not that it's not well defined. It's not defined at all. You cannot talk about rotation or spin or anything of something that is conceptually made of a single piece. Okay, not even God can rotate that which is made of a single piece, because you would have to have at least 2 points within that object, right? For example, a point on the outside, a point on the inside, right? And you can say, okay, this point rotates or spins, with respect to this one. You don't, because it's a single particle. There is no second point to it. Okay, and this is the problem with using a fundamental particle and talking about spin. There's a contradiction there. Okay, they say, well, we cannot exactly tell you. No, it's not that exact. You can't. It's impossible. It's irrational to try to say that a fundamental particle spins, period. Okay, so don't talk about spin, which is a physical property, and you apply it to this thingy, which is not even a particle, which is a concept, okay, an abstract mathematical concept. It's a number. That's all they see. Okay, they talk about the mass, the charge, right? 1.6 times 10 to the minus 19 coulombs. That's what an electron is for a mathematician. It's a number followed by a unit. Okay, it's just a relation with respect to other constants or things that they've measured and established there, Okay, so here we have another fellow. His name is James Lincoln, and he's from UCLA, and he's going to show you what spin is. He says spin, but then he illustrates it is spin. There you see him moving his hands. Okay, so they say that spin is not spin, and they all illustrate spin as spin. There you see him. What is it doing? Spinning, right? And he's saying that, and there he shows it. He's twirling it, right? Okay, that's how he's saying that the electrons orbit the nucleus, but you can see how he's going to spin them. Okay, so this is the issue. The issue is that all these people have a contradiction, and that's because they cannot picture anything in the quantum world. They say electron is a particle. It's a elementary fundamental particle, meaning it's not made of anything, meaning it's made of a single piece, right? That's what they mean. And then they talk about spin, about rotation around an axis. This is a mathematical concept. You can't do that with a particle that is made of a single piece. It's got nothing to rotate around. There is no, you can't divide it and say, well, I'm going to put an axis and I'm going to put a point on the outside of it and say that the point rotates with respect to the axis. Not for a particle that's made of a single piece, because you're in effect saying it's made of at least two pieces, a centerpiece and an edge. And you're violating your hypothesis. Your hypothesis was that it was made of a single piece, remember? And now you're saying, no, it's made of two pieces. One on the outside, one on the inside. This one rotates around the inside. You can't do that because you get a contradiction. Okay? These people don't understand these things because they never do physics. What they're thinking about is math. They're thinking about equations. They're thinking about numbers and units. They're not thinking about physics. They're not picturing. They're not visualizing what they're saying. Okay, so here we have, let's go with electron spin the way the mathematicians do it. Okay, here it is. Here you have an electron, and it's supposedly made out of a single piece. I color-coded it just so that you could see spinning of a particle made of a single piece. You got to think of this thing as made of a single piece, even though I color-coded it so that you can see the spin, okay? So that's our starting point, okay? Here we have it rolling around the proton, okay? That's your hydrogen atom there, okay? So we have the little ball on the outside. It's spinning, right? And it's also rotating or orbiting the proton, which is also, I guess, spinning, right, around an axis. Okay, so that's the situation. And that's their atom. Okay, that's what they imagine, this planetary atom. Okay, so keep that in mind. This is how they picture these things. And so the question is, okay, let's concede, because see, this Lincoln guy says he can explain magnetism, right, with this electron spin. He says, oh, we discovered that every time that there's attraction, it's because the electrons on each of the two magnets that are attracting each other are spinning. Okay, let's concede. Okay, so they spin. Okay, so the electrons are spinning. Tell me how the spinning of the electrons in each magnet cause attraction from a distance. Okay? And here I try to illustrate it for you, okay? Okay, you have the electrons going around their protons, and we illustrate this as hydrogen atoms, obviously, right? Because we're trying to simplify, we're trying to get the mechanism only. Okay, so they're spinning and they're orbiting their respective protons on two magnets. Why or how, by what mechanism does one magnet attract the other now that we have, your electron spins? Okay, just tell me that every time that a magnet attracts another, you notice that the electrons are spinning and they're orbiting their atoms. Fine. And they're all aligned, no problem. Tell me how this produces attraction from a distance. Okay, and this is the problem. The problem is that they give you a description, but not an explanation. They cannot tell you how the electrons do this from a distance. Here we have two magnets, right? Little guys there, the two dark ones, okay? And so the question is, here the electrons are spinning for each one of the magnets. Okay, great, no problem, I'll concede. Okay, and so the question is, why is this already pulling on me from a distance? I mean, the electron stretches across that divide. So this is the problem. The problem is they cannot explain the mechanism. And they say that's philosophy. We don't do that. And if you don't do that, why did you even try? Why did you try to convince me that with electron spin you can explain attraction between two magnets? You can't. You can't, because you can't do it with discrete particles, which ain't particles in quantum physics. They're just values. They call them particles, but they're values. That's all they are. They're numbers. They're numbers followed by units. They're talking about energy and charge and fields and mass and nonsense that has nothing to do with physics. In physics, you got to have the object. If you're going to talk about balls, okay, tell me how a ball attracts another ball from a distance. And the answer is you can't. You need to have some connection there, physical connection. And you say, Bill, why do you say that there's a connection here? I can't see or touch anything in between. I can't see or touch the mediator. And the answer is very simple. The answer is that if you don't put a mediator in there, you're doing so-called physics with black magic, with, witchcraft. That's what you're saying. You're saying that you're going, ooh, and it happens. It does happen no matter what. You're doing it with black magic. And so this is the problem. You have to put a mediator in there, a physical mediator that you cannot see or touch, because a mediator is not that which you can see or touch. It's that which has shape. There's something there, elongated thing, uniting these atoms, right? And we can't see or touch it. You have to arrive at a different hypothesis, a different starting point. And then you can start explaining things, because you don't need magic now. You don't need to say, well, this particle, discrete particle affected that discrete particle from a distance. You can't say that, not in physics. You can say that in religion, but not in physics. Okay, so here we have a spiraling atom. Someone sent me a question there, or says, if all atoms in the universe are connected, what happens to those gazillions of threads in a rotating object like a star or a planet? Do they stack up indefinitely? If so, the objects would gain mass and volume. It would be like a snowball picking up more snow and getting bigger as it rolls down a hill. So this fellow, again, he's thinking in terms of see and touch. That's the whole issue. They say, well, if this wraps around, it means it's touching, right, the thread and just rolling it around. Okay? And so this is the first problem here. Okay, here, let me show you. The definition of the word object destroys all religions. I say that, okay? Okay, that's the first issue. And the second issue, an object is not that which you can see or touch. Okay, so whenever you use the notion of see and touch, that's when you're going to run into trouble. You got to get rid of touch. Don't bring see and touch into physics, okay, because it's not about see and touch. An object is that which has shape. All objects have shape in the universe. All objects, all atoms have shape. What not all things in the universe are not. They cannot all be seen and that cannot all be touched. You can't see the air. It's made out of atoms. You can't see it. Imagine the ropes that connect, two atoms, which is gazillions of times thinner than, the diameter of an atom. And so, yeah, you got to put it in that context. You can't see or touch. You cannot bring the see-touch criteria and try to debunk, the rope model. Besides, we don't care about debunking. There is no debunking in science, really. In science, you criticize and you explain. And it's the explanation part that forms a part of science. Criticism, you can criticize. If you have a good argument, you can try to destroy a theory and say that's not correct. That's in violation of Mother Nature, right? But hopefully you can put something in exchange, because if you do not explain, if you do not propose something in exchange, you're not a scientist. A critic is not a scientist. A skeptic is not a scientist. The scientist is the guy who explains. Okay, so let's get that right. We don't debunk. Okay, what we do is we criticize, but propose something in exchange to replace it, to say, I'll tell you why yours is irrational. Okay, it's not that it's wrong, it's irrational. And especially in the case of mathematical physics, if you're going to be moving concepts around, like mass and charge and fields, well, then, we need to take you in with the men with white jackets. We do not move concepts in physics. Physics, you have to have objects, and you have to have a replacement for what the other guy proposed. You're not the critic who's in the crowd watching the fight. You're the boxer who's inside the fight. You're the guy in there. That's the scientist. Right? Shape is a universal property of object. There is no object you can imagine that doesn't have shape. Concepts don't have shape. Okay? Not a single concept has shape. Okay, but if you know of any concept that has shape, man, let me know. Okay, so here we have a simulation to try to show you how an atom looks like under the rope model. Okay, and this was made by my good friend Dan Ferguson, right? Took the trouble to draw that atom there in the center, and I've used that quite a bit, so I thank him tremendously for his job, right, for his work. Anyways, here we have the atom. That's more or less what we think the atom, hydrogen atom, looks like. Okay, we have a star in the center, that's the proton, and it's surrounded by this membrane, which is weaved by countless threads, not ropes, threads, okay? And so we have the threads making the star and the threads making the membrane that encapsulates the star. And then what comes towards that are ropes, not threads, but ropes, twine threads, okay? So we have ropes coming towards the edge of the atom. They fork out. One goes to the center and becomes, the blue ones in this case, right? Goes to the center and becomes part of the proton. And the red ones, they weave around and they form the membrane that encapsulates the proton star. There's no positive, there's no negative. We don't know what that is in physics. Mother Nature has no clue when they talk about positive and negative. Okay, okay, so that's our atom. Okay, that's the one we propose. Okay, we're saying that it's not the planetary atom, it's this atom that you see there. Okay, and here we have okay, I don't have it. I was going to show you quantum jumping. I just want to show you that that same atom expands and contracts. Okay, and so keep this in mind for this notion of spin. Okay, so it's going to expand and contract. Is the electron spinning? Electron shell, is it spinning around the proton star? That's the question. Okay, do electrons spin? And we're not talking about a little bead that's on the outside, elementary particle that is moving around, spinning. We're not talking about that. We're saying the electron is a membrane. And whenever they talk about the bead, what they're really pointing to is a location on the membrane. Okay? So that's what they've confused for the electron bead. Okay, but we have this. Does the whole thing rotate? Does the electron, the whole electron membrane spin around, the center axis? And my guess it doesn't. Okay, and again, I'm making the assumption that it doesn't. You have to think of it more or less like this. Okay, what it's doing is you have all these threads, right? The what we call the magnetic thread, arbitrarily using the word magnetic just to be consistent with the past, so that we don't change the wording. We try to keep as much with the wording as possible. So we use the electron thread to make the proton star, and we use the magnetic thread to make the encapsulating membrane, balloon, right? But this balloon is not a smooth balloon. It's made out of threads. The threads are not, stretched out in the sense that they're, straight or smooth. They're corrugated. They're bent a little bit all around. Okay, and what you have is this thread which is torquing all around the electron shell. So all these threads, they're wound around the electron shell, and they're corrugated to some degree. They're not in a straight line, and they're twirling in situ. Okay, so when they measure or they detect the electron at a given point, the electron shell at a given point, they say, oh, the electron is spinning. No, it's not spinning. What it's doing is moving around, like more or less, I'll do it with a rope. It's not exactly this, but it's doing this, in situ. It's just moving around in situ. Okay, that's what it's doing. And so it's not that the shell rotates, but that the electron thread is going all around, the magnetic thread, is going all around, and it's twirling in situ. Okay, and this gives a sense that there is motion of not only locally of the electron bead, all right, quantum mechanics, but also of the whole shell. Gives an idea that the whole thing is maybe spinning or rotating. And I don't think that's the case. I think that the reason there is such speed in the spinning of the electron is because it's going nowhere. It's doing it in situ, just moving around, at great speeds, perhaps at the speed of light, and so they say, oh, it's spinning, but we don't know what spin is. And it's a wave property. Yeah, it is a wave property because we're talking about a little thread that has a waviness to it, and it's spinning in situ. And that's why it's so fast. It goes, it goes all around and also in situ at a great speed because that's how fast it's moving. Okay, and this is probably the best way to picture it. So, okay, so that's my take on that. I can say that, here's maybe a couple more that you can ponder so that you can try to visualize this. Here it is. Okay, here's, you can imagine the ropes converging upon this ball, and the locations that you see there, they're not moving. The thread, that piece of thread is not moving really. What it's doing is turning in situ. It probably moves a little bit anyways, forward or backward, but primarily it's spinning in situ, and that's what gives them the idea that there's an electron spinning locally, and that it's made out of a single piece. It's infinitesimally small, right? Because that's what they're really, what's in front of them, but which they can't see. This is something you have to imagine, you have to visualize. We'll never be able to see this stuff. It's just for food for thought. It's for you to comprehend it, understand it, and say, well, maybe that's the way it is out there in this secret world of Mother Nature's atom. And that's the best we can say for spin.